Let's think about work and how to quantify it based on what we see on a graph. Let's take a simple case and then we'll expand from there. Let's talk about an isobaric expansion. So that means constant pressure. Let's say my initial volume is here. That's my starting volume. And here's my final volume here, because I'm expanding this. And let's say I'm at this pressure, constant pressure, remember. So I start here, I expand to here on the pressure volume diagram. We could call this delta V. And this is P, and work is P delta V. Actually, negative P delta V. Look at this rectangle. This rectangle has a height of P and a length of delta V. So the area of this rectangle, the area under the graph, essentially, is equal to work. So on a pressure volume diagram, we can see from this simple rectangle that the area under the pressure volume curve, that's equal to work. Now, if this was an isobaric compression instead of an expansion, the volume would be the same. Instead of this being your start and this being your end, this would be your start and this would be your end. So the rectangle would have the same dimensions. The difference would be that the work would now be positive because the change in volume would be negative. It would have gone from a high volume to a low volume. So same size, just different sign. When work is done on some system, then the sign is positive because it's an increase in energy. And when work is done by the system, the sign is negative because the system loses energy to the surroundings. There isn't any reason to believe that we couldn't take this general idea and expand it to curves and other kinds of shapes. Like, for example, during an isothermal expansion, here's my starting point, here's my ending point. This is a pressure volume curve, so if I could find the area under this curve, that would be equal to the work. Same thing would be true for an adiabatic expansion. My starting point's here, my ending point's here. If I could find a way to determine the area under that curve, that would be equal to work. What we often see happening, and this is where this becomes quite useful, is we see systems, human-made systems, that operate in cycles. And these thermodynamic cycles make use of several processes in a row. Now, let's say we had this cycle going on. We started here, and we went through here, and we actually ended back at the starting point. That's a cycle. Well, take a look at what's going on in this cycle in terms of how much work is done. In this process, this expansion, the system does work on the surroundings. How much work is it? Well, it's this amount of work. I could graph that amount of work. Then during this adiabatic expansion, this amount of work is done. The crosshatched part. That's how much work is done in that expansion. Now, as we go back, as we compress, as we go from here to here, in the third stage of this cycle, work is now done on the system. So I would have to subtract energy here, and then there's an adiabatic compression at the very end, and this amount of work was done on the system. What this really means is all these areas added up turn into this. The area inside this curve is the net result of all the work done by the system minus the work done on the system. So the work done is just the area inside that curve.